The particle has to be charged, cannot be neutral like a neutron, and it has to be moving. It cannot be stationary. It cannot be taking a siesta. Here's our situation. We have a magnetic field directly out of the plane of the sketch towards you. That's indicated by that encircled dot, as though you're looking at an arrow that's been shot directly towards you. I have a particle on the left and a particle on the right, one positive, the other negative. They both have velocity upward in our snapshot, our freeze frame. And off to the right of the screen, I give you some data. The charge, it looks like I have either a proton or an electron because I have the elementary amount of charge, 1.6 e negative 19 coulombs. I give you the strength of the magnetic field and the speed of the particle. Here's the equation for the magnetic force. I want you to understand that this is a vector equation. I can't draw those cute little arrows overhead in this presentation. There really should be one of those cute arrows over the F and the V for velocity and the B for magnetic field, but I just can't draw them. Also, that is V cross B. That's a cross product. And then I have the Q out front. So that's the vector equation. If I just want the magnitude of the magnetic force, I will use this. It's an expansion of a cross product that we saw back in an earlier chapter. And just so that that Q cannot be negative, because this is supposed to be a formula for magnitude only, I'll bracket that Q to make sure that I only get a positive value out of it. Now, the cross product, back to the vector equation. I need to determine the direction of F by using a right-hand rule. I will then use the formula for magnitude to get the magnitude of the force. But first up, the direction, and this is the part that's hard for most people, is using your right hand to determine the direction of a vector. I'm showing how I'm going to use my right hand here. You put your knuckles up against the screen and your fingers straight up the screen to be in the direction of velocity, because that's the first vector in the cross product. You then are going to curl your fingertips away from the screen and toward your face so that they are then in the direction of the magnetic field vector, which is the second vector in the cross product. The thumb of your outstretched hitchhiking thumb gives you the direction of the cross product, the vector that results from the cross product, and that's V cross B off to your right. That's going to be true for both of my particles here. I don't care anything about their signs so far. They both are traveling upward in the picture. They're going through this magnetic field, which is out of the plane of the page or screen toward your face. So the V cross B is going to be exactly the same for the two particles. I've shown that vector in this slide here. But now comes the tricky part, to determine the direction of the force vector. And what you have to worry about is that Q that's sitting in the vector equation, is it positive or negative? Because look, if it's positive, then the F vector is in the same direction as the V cross B vector. But if the Q is negative, the F vector is flipped or reversed from the direction of the V cross B vector. For the particle on the left, which is positive, the F vector is in the same direction as V cross B. No flipping going on here, but on the negative, on the right side of the screen for the negative particle, the F vector is flipped or reversed from the direction of the V cross B vector. Now, once I get the direction straight by using my right-hand rule for cross products, let's go after the magnitude of those two force vectors. I'm going to plug in the charge, the speed, or magnitude of velocity, the magnitude of the magnetic field, and the fact that the angle, theta, which is always the angle between the two vectors in the cross product, that angle is 90 degrees here because V is up the screen and the magnetic field vector is directly off the screen, perpendicular to the screen towards your face. Angle between 90 degrees. And there we get the magnitude of the force. So now we've got both direction and magnitude for the magnetic force that acts on the positive particle and the magnetic force that acts on the negative particle. Let's do a little three-step summary. The magnetic force on a moving charged particle, and you've got to have charge and it has to be moving, no siestas here, is given by this vector equation, which involves a vector cross product. If the Q is positive, then the force and the V cross B vectors are in the same direction. But if the Q is negative, they are in opposite directions. So when you get to an exam or a homework problem and you're trying to figure out the force acting on a moving charged particle, you have to read the sentence carefully. Are we told the charge directly? Maybe we have an explicitly shown plus or minus sign. Or is the information there subtly, like we're told that we have an electron, which means negative charge, or a proton, which means positive charge. So you have to look and then be careful. That's it for our little quick explanation of magnetic force on a moving charged particle.